The National Electrical Code allows the use of crimp-type butt splices for grounding conductors under certain conditions. Firstly, the splice is not located in a damp or wet location. Secondly, the splice is made with a splice listed for the type of grounding conductor being used. Thirdly, the splice is properly installed according to the manufacturer's instructions. While crimp-type butt splices are technically allowed by code, they are generally not considered best practice for grounding conductors for several reasons. Crimp splices create a higher resistance connection than a welded or soldered splice. This can increase the potential for voltage drops and ground faults. Crimp splices are more susceptible to corrosion and oxidation over time, which can further degrade the connection. Welded or soldered splices are considered more reliable and long-lasting than crimp splices. For best results, it is recommended to use the following methods for splicing grounding conductors. Welded splices are the most reliable and permanent splice method. Soldered splices are also very reliable and provide a low resistance connection. A split bolt connector provides a secure and weather-resistant connection. When making a splice in a grounding conductor, several factors must be considered to ensure a safe and effective electrical system. The grounding conductor's primary purpose is to provide a low-impedance path for fault current, allowing protective devices like circuit breakers or fuses to quickly trip and clear fault. This protects people and equipment from electrical shock and damage. The National Electrical Code, or NEC, provides guidelines for proper grounding and bonding practices. These guidelines are intended to minimize electrical hazards and ensure the reliable operation of electrical systems. The NEC permits the use of various methods for splicing grounding conductors, but it's essential to understand the code's requirements and industry best practices to make informed decisions about which splicing method to use. Let's delve deeper into the specific requirements and considerations for splicing grounding conductors. One crucial code requirement is that the splice must be listed for the specific type of grounding conductor being used. This means that the splice connector has been tested and approved by a recognized testing laboratory, such as Underwriters Laboratories, or all, for use with the particular type of grounding conductor material, such as copper or aluminum. Using a listed splice ensures that the connection is mechanically and electrically sound and can withstand the stresses and environmental conditions it may be exposed to. Another critical requirement is that the splice must be properly installed according to the manufacturer's instructions. This includes using the correct tools and techniques to make a secure and reliable connection. The manufacturer's instructions will specify the proper torque or crimping force to apply to the connector, as well as any other specific requirements for installation. Following the manufacturer's instructions is essential to ensure that the splice is properly made and will perform as intended. While the NEC permits the use of crimp-type butt splices for grounding conductors under certain conditions, it's generally not considered best practice for several reasons. Firstly, crimp splices create a higher resistance connection than welded or soldered splices. This increased resistance can impede the flow of fault current, potentially slowing down the response time of protective devices and increasing the risk of electrical shock or damage. Secondly, crimp splices are more susceptible to corrosion and oxidation over time, especially in damp or wet environments. Corrosion and oxidation can further degrade the connection, increasing its resistance and reducing its reliability. This can lead to a gradual deterioration of the grounding system, compromising its effectiveness over time. Thirdly, welded or soldered splices are generally considered more reliable and long-lasting than crimp splices. Welded and soldered connections create a permanent low-resistance bond between the conductors, providing a more robust and reliable connection that is less susceptible to corrosion and oxidation. Given these considerations, it's generally recommended to avoid using crimp-type butt splices for grounding conductors whenever possible. Instead, opt for welded, soldered, or split-bolt connectors, which offer superior performance and reliability. Welding is the most reliable and permanent splice method for grounding conductors. It involves fusing the conductors together using heat, creating a continuous, low-resistance connection. Welding is particularly well suited for large grounding conductors and applications where a high degree of reliability is required. Soldering is another excellent option for splicing grounding conductors. It involves using a molten solder to create a metallurgical bond between the conductors. Soldering provides a low-resistance connection that is resistant to corrosion and oxidation. Soldering is a good choice for smaller grounding conductors and applications where a permanent, reliable connection is needed. Split bolt connectors are mechanical connectors that clamp the conductors together using a bolt and nut. Split bolt connectors are easy to install and provide a secure, weather-resistant connection. They are a good option for applications where welding or soldering is not practical or feasible. When selecting a splicing method for grounding conductors, it's essential to consider the specific application and the environmental conditions. For example, in damp or wet locations, it's crucial to use a splicing method that is resistant to corrosion and oxidation. In high vibration environments, it's important to use a splicing method that is mechanically robust and can withstand the stresses of vibration. In addition to the splicing method, it's also essential to ensure that the grounding conductors are properly sized and installed. The size of the grounding conductor must be adequate to carry the maximum fault current that may occur in the circuit. The grounding conductor must also be installed in a manner that provides a low impedance path to ground. This typically involves running the grounding conductor along with the circuit conductors and bonding it to metal enclosures and equipment. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the code requirements and industry best practices, you can minimize electrical hazards and ensure that your electrical system operates safely and effectively. In summary, while crimp-type butt splices are technically permitted by the NEC for splicing grounding conductors under certain conditions, they are generally not considered best practice due to their high resistance, susceptibility to corrosion and oxidation, and low reliability compared to welded, soldered, or split bolt connectors. When splicing grounding conductors, it's generally recommended to opt for these preferred methods to ensure a more reliable and long-lasting connection, reducing the risk of future problems. Remember to always follow the manufacturer's instructions and applicable codes and standards when working with electrical systems. If you're not comfortable performing electrical work yourself, it's best to consult with a qualified electrician to ensure that the work is done safely and correctly. Electrical work can be dangerous, and it's essential to take the necessary precautions to protect yourself and others from electrical shock and fire hazards. Here's a more detailed look at each of the recommended splicing methods. Firstly, welding. Welding grounding conductors involves creating a strong, permanent connection by fusing the metals together. This method is generally considered the most reliable because it provides a continuous, low-resistance path for fault current. There are two main types of welding commonly used for grounding conductors: exothermic welding and arc welding. Exothermic welding, also known as CAD welding, uses a chemical reaction to generate heat and melt the metals together. This process is often used for creating ground connections in soil or concrete because it doesn't require an external power source. Arc welding, on the other hand, uses an electric arc to melt the metals together. This method is typically used for welding grounding conductors in more accessible locations. When welding grounding conductors, it's essential to follow proper safety precautions, including wearing appropriate protective gear, such as a welding helmet, gloves, and a fire-resistant jacket. It's also important to ensure that the area is well ventilated to prevent the buildup of hazardous fumes. Secondly, soldering. Soldering grounding conductors involves using a filler metal, typically a lead tin alloy, to create a conductive bond between the conductors. This method is less permanent than welding, but it still provides a reliable, low-resistance connection. Soldering is generally used for smaller grounding conductors and applications where welding is not practical. When soldering grounding conductors, it's essential to use a soldering iron or gun with sufficient wattage to heat the conductors to the proper temperature. It's also important to use a flux to clean the surfaces of the conductors and promote the flow of solder. Proper ventilation is necessary to avoid inhaling harmful fumes. Thirdly, split bolt connectors. Split bolt connectors are mechanical connectors that use the bolt and nut to clamp the grounding conductors together. These connectors are relatively easy to install and can be used for a wide range of conductor sizes. Split bolt connectors are often used for making temporary ground connections or for splicing grounding conductors in locations where welding or soldering is not feasible. When using split bolt connectors, it's essential to ensure that the conductors are properly cleaned and that the connector is tightened to the manufacturer's specified torque. Over-tightening the connector can damage the conductors, while under-tightening can result in a loose connection. In addition to the splicing method, the type of grounding conductor being used can also impact the choice of splicing materials and techniques. Grounding conductors are typically made of copper or aluminum, and each material has its own unique properties. Copper grounding conductors are highly conductive and resistant to corrosion, making them a popular choice for many applications. However, copper is also more expensive than aluminum. Aluminum grounding conductors are lighter and less expensive than copper, but they are also less conductive and more susceptible to corrosion. When using aluminum grounding conductors, it's important to use connectors and splicing materials that are specifically designed for use with aluminum to prevent galvanic corrosion. Galvanic corrosion occurs when two dissimilar metals are in contact in the presence of an electrolyte, such as moisture. The more active metal will corrode, while the less active metal will be protected. In the case of aluminum and copper, aluminum is the more active metal and will corrode if it's in contact with copper in the presence of moisture. To prevent galvanic corrosion, it's important to use connectors and splicing materials that are made of the same metal as the grounding conductor or that are specifically designed to prevent galvanic corrosion. When metallic connectors, for example, have a barrier between the aluminum and copper components to prevent direct contact. Another important consideration when splicing grounding conductors is the environment in which the splice will be located. If the splice is located in a damp or wet environment, it's important to use a splicing method and materials that are resistant to corrosion and moisture. Heat shrink tubing, for example, can be used to seal the splice and protect it from moisture. It's also important to ensure that the splice is properly supported and protected from mechanical damage. Grounding conductors should be routed along with the circuit conductors and secured to prevent them from becoming loose or damaged. In summary, splicing grounding conductors requires careful consideration of several factors, including the code requirements, industry best practices, the type of grounding conductor being used, and the environment in which the splice will be located. By following these guidelines, you can ensure that your grounding system is safe, reliable, and effective. Here are some additional tips for splicing grounding conductors. Ensure that the grounding conductors are properly sized for the application. The size of the grounding conductor should be based on the size of the circuit conductors and the fault current that the grounding conductor is expected to carry. Always follow the manufacturer's instructions when installing connectors and splicing materials. The manufacturer's instructions will provide specific guidance on how to properly install the connector and ensure a reliable connection. Use a torque wrench to tighten connectors to the manufacturer's specified torque. Over-tightening or under-tightening connectors can damage the conductors and result in a loose connection. Inspect splices regularly to ensure that they are in good condition. Look for signs of corrosion, damage, or looseness. If you find any problems, repair or replace the splice immediately. Keep detailed records of all grounding system work, including the date of the work, the materials used, and the location of the splices. This information can be helpful for future maintenance and troubleshooting. Finally, it is crucial to emphasize the importance of seeking professional assistance when dealing with electrical work, particularly when it comes to grounding systems. Grounding systems are critical for ensuring the safety of electrical installations and protecting individuals from electric shock. Incorrectly installed or improperly maintained grounding systems can have severe consequences, potentially leading to electrical hazards, equipment damage, and even loss of life. Therefore, it is always best to consult with a qualified and licensed electrician who has the knowledge, skills, and experience to perform grounding system work safely and effectively. A professional electrician will be able to assess the specific requirements of your electrical system, select the appropriate grounding methods and materials, and ensure that the grounding system is installed in accordance with all applicable codes and regulations. They will also be able to perform regular inspections and maintenance to keep your grounding system in optimal condition. Attempting to perform grounding system work without the proper training and experience can be extremely dangerous. Electrical work involves inherent risks, and even seemingly minor mistakes can have serious consequences. By entrusting grounding system work to a qualified professional, you can have peace of mind knowing that the work is being done safely and correctly, protecting yourself, your family, and your property from electrical hazards. In addition to the technical aspects of splicing grounding conductors, it's also important to consider the legal and regulatory requirements. Electrical work is typically regulated by local, state, and national codes and standards. These codes and standards are designed to ensure the safety and reliability of electrical installations. Before performing any electrical work, it's essential to familiarize yourself with the applicable codes and standards and ensure that your work complies with these requirements. Failure to comply with electrical codes and standards can result in fines, penalties, and even legal action. It's also important to obtain any necessary permits before starting electrical work. Permits are typically required for new electrical installations, modifications to existing installations, and repairs that involve significant changes to the electrical system. Obtaining a permit ensures that the work is inspected by a qualified electrical inspector to verify that it complies with the applicable codes and standards. In conclusion, splicing grounding conductors is a critical task that requires careful consideration of several factors, including the code requirements, industry best practices, the type of grounding conductor being used, and the environment in which the splice will be located. By following these guidelines and seeking professional assistance when necessary, you can ensure that your grounding system is safe, reliable, and effective. Remember, electrical safety is paramount, and it's always better to err on the side of caution when dealing with electrical work.